Let's discuss a question from gas turbine. So here basically what is given is that the compressor is driven by the high pressure turbine, and the low pressure turbine takes care of the load. Okay, so let's first draw the Brayton cycle, okay, in a TS diagram. So first you have a compression, and then the heat combustion in boiler, combustion in the boiler, boiler or the combustion chamber, and then you have a the high pressure turbine, and then the low pressure turbine, and then back to compressor. Okay, so this is 1, this is 2, this is 3. 3 to 4 is high pressure turbine, 4 to 5 is low pressure turbine. So 3 to 4, whatever work done, that takes care of the compressor. That's what is given. So whatever the work that is produced by 3 to 4 turbine, high pressure turbine, that takes care of the compressor, whereas 4 to 5 increases the enthalpy, and that the exhaust gas at enthalpy that goes again to the nozzle, and that's what you get the proper thrust depending on the application. So what we are interested in here is temperature of the exhaust gas from the unit. So you need to find out the temperature at the 5, that is unit in the sense both low and high pressure turbine together is one unit. So T5 is something which you got to find out. Okay, and compression ratio is given as 4, which means P2 by P1 is 4, and also your P3 by P5 is 4, that is entry of the high pressure turbine by exit of the low pressure turbine, that is P3 by P5, that is also 4. So now, and also the mean temperature is 300 Kelvin, and the max temperature, that is T3, is 1000. Okay, that is 1000 T3. So T2 is something which we don't know. Okay, so what here? So one information we have is that the work done by in 3 to 4 is equal to 2 and 1. So that we can utilize, right? But for that we need to know the temperatures at 2 and 4. So let's first find out the temperatures in 2 and 4. So temperatures, how they are related. 1 and 2 is basically adiabatic compression. So adiabatic laws will hold. PV power gamma is 0. And we assume that the air is ideal gas here, so PV is equal to MRT. So from these two equations, okay, we need to get a equation which relates T and P. So when you substitute V as MRT by P here, so what you get is T power gamma is P power gamma minus 1 is equal to some constant, right? So from this basically you can get back to this equation. T2 by T1 is P2 by P1 whole power gamma minus 1 by gamma. This is something which is always you have to use when you are dealing with reversible adiabatic process. So P2 by P4 is 4 and gamma is 1.4, so 0.4 by 1.4, and so T1 is 300, so 300 into, remember we are dealing with Kelvin, so 300 into this 4 into 0.4 by 1.4. So this value you get as this value will be getting as, so this we get as 445.8 Kelvin. Okay, so this is T2. Now how do I get T4? Okay, so now we'll use that statement that work done in compressor, that is work done from 1 to 2, work requirement from 1 to 2 is work done by high pressure HPT, that is high pressure turbine, which is from 3 to 4. Okay, so work done in compressor would be H2. So because here it's reversible adiabatic, so whatever work you're doing in an open system process, that is change in enthalpy. So H2 minus H1 will be equal to H3, decrease in the enthalpy in the turbine. So H2 minus H1 is MCP T2 minus T1, and this is nothing but MCP, though the CP will change with the temperature, but here we are dealing with the ideal system, so Cp doesn't change. We assume that Cp doesn't change. So T2, basically T2 minus T1 is equal to T3 minus T4. Okay, so we know T2, we just got 440.8 minus 300 is equal to T3 is 1000 minus T4. So from this we get T4 as 1000 minus 444 minus 8 plus 300. So we get T4 as 854.2 Kelvin. So once we got T4, so we need to find out T5, remember that. So between 3 and 5 we can apply the same equations, T3 by T5 by P3 by P5 whole power 0.4 by gamma minus 1 by gamma. So this you can apply, but the thing is that we don't know P3 by P5. We know P3 by P5, which is nothing. Yeah, we know that P3 by P5, that is 4. So 0.4 by 1.4, and T3 is something which we know here. I mean, in fact, you need not do all this. I mean, T3 by T5 you can apply. Okay, so from this actually, so in fact there are two ways of doing it. Directly you can apply between T3 and T5 this equation. T3 is already known 1000 and T5 by 4 into 0.4 by 1.4. So from this directly, I mean, instead of just doing this compressor work requirement is equal to HP, instead of that directly, if you from the first go, if you do this, you will get T5 as 670 to 673, close to 673. Okay, but if you want to do from this way, once you get T4, then T4 by T5 you got to apply, which is nothing but P4 by P5, and P4 by P5 is nothing but your P4 by P5 you don't know, but you know that P3 by P5. From this, what you can do is P4 by P5 you can write as P4 by P3, okay, and P3 by P2, P3 by P5. So P3 by P5 you already know, right, which is nothing but so this is actually a complicated way. I mean, you can do it like this, but P3 by P5 is again your 4, okay, and P4 by P3 is something which you already got. Okay, so this is bit complicated, I would say. I mean, the direct way is this, which would give you 673. 673 is the answer. So it's direct. I mean, you need not actually do all that at the start. So what you have to do is just go to this part of the solution. Okay, you can forget about the right hand side part. So because this holds only because 3 to 4 and 4 to 5 is a straight line. So basically 3 to 5 is also a straight line, and directly between 3 and 5 you can apply the temperature and the pressure law. Basically this law you can directly apply. This law you can directly apply between T3 and T5, because 3 is something which you know, and 5 is also which you need to find out, and the pressure ratio between 3 and 5 is the 4. So directly, instead of going into the compressor work and all that, because that will again complicate, and again you will just end up doing the same thing. But here is the shortcut. Directly apply between T3 and 3 and 5, just apply the temperature and the pressure relation, and directly you get T5, which is 673. Thank you.